Alright, so that last example started to get me into when do limits not exist. So if the limit does not exist when the number L is one of the satisfying conditions of the definition, then we say that the limit as x approaches c does not exist. So limits typically fail for three reasons. One, f of x approaches a different number from the right side of c than it does from the left side, like we saw before. Approaches to 1 and 7. F of x could increase or decrease without bound as x approaches c. So that would be more along the lines of when we have an asymptote, specifically a vertical asymptote. Oops. And when f of x oscillates between a fixed point as x approaches c, kind of like your sine and cosine functions will oscillate in between -1 and +1, that type of deal. So let's explore some of these special cases when limits don't exist. So the first thing I'm going to do is I'm going to graph this mess. I'm at least going to type it into my calculator as my y1. Alright, so graphing this, my graph should end up looking something like this. Note your calculator is not going to show that you have holes really largely on your calculator. It's just going to suddenly split. Alright, so if you'd like to use a table instead, you should see that your y values from the left are -1 and your y values from the right are +1. Alright, so what ends up happening is that all of a sudden I have this gash to where I'm definitely not approaching the same thing from the left and from the right. That's a problem. So we don't know what this is approaching. So my limit from the left and right, well, my left limit is -1. My right limit's definitely +1. But my limit at 0 is not existent. Because that left and right limit are different. So your left and right limits are different. That's a bad case. Alright, let's look at the next one. So this is just that parent function of y is equal to x1/x². So all that's going to happen is I'm going to take this parent function, I'm going to shift it to the right. So that parent function looked something like, okay, I've got an asymptote sitting here, and then I had a little wee-oop graph, and that was it. So we're just going to take that and we're going to shift it to the right, which means that my asymptote, instead of being at 0, is now going to be at 1. And again, when in doubt, t-chart it out, that's cool. So at 2, I should get the point of 1. At 0, I should also get the point of 1, because I can get 1/1. From there, I get some very ugly numbers. Again, I always approach that vertical asymptote. I never actually touch it. If I wanted to t-chart very closely, I definitely can. T-charting this out. When I type in 0, I get 1, 4, 100, 10,000, 1 million. So many zeros, so little space. Alright. Don't know what it is at 1. If I type in 1.001, again, I'm going to have that 1 million. Alright, my computer just doesn't like to write that small. If I type in 1.01, that is going to be 10,000 again. If I type in 1.1, I'd get 100. If I type in 1.5, it should be 100. No, it should be 4. Sorry, just looked at my previous y value. And then finally at 2, I should get 1. Alright, so what is happening? Well, from the left side, it is getting larger and larger and larger and larger and larger and larger each time. And it's not really approaching any one number, it's just getting infinitely larger, which is a problem. And then from the right side of my graph, that same thing is happening. I'm not approaching any one number. It's just getting gigantic really, really quick, which is kind of intimidating. So, because of this, it's not approaching any one number. It would not exist. Because it is increasing without bound. Alright, so that's what that looks like. Alright, just give me a little sentence. Tell me, what's going on. Calculus is going to be looking for a lot of your guys' reasoning skills, just like in geometry. You had to write it out why this was. You're kind of proving without proving that you know your Alright? So, just make sure you back your stuff up. Alright, the next one. Highly recommend typing this into your calculator, just because it gets gross. If you really want to think about this, this is actually sine of x to the negative 1. Is another way to think about that, but yeah, I'm just going to type it in. So, typing this in, you'll see that I only have a chart. There's a reason. Alright, so as I'm looking at these numbers, please notice that each time these fractions are getting smaller and smaller and smaller. We know that, 1/4 is smaller than 1/2 because, well, hopefully we know that at this point. Alright, so as your denominator increases, your amount that you actually have decreases. So now I get to go and type these into my ask function. So technically what I have on this first one, for example, is the limit of x approaches 0 of sine of 1/2 divided by pi. Copy dot flip or keep change flip would put me at now pi over 2. Alright, and we know what sine of pi over 2 is, and that's just 1. Alright, same type of deal. I'd go around my unit circle and find, okay, that's going to be negative 1, copy dot flip, all of that kind of stuff. 5 pi halves would end up being at 1, negative 1, 1, negative 1, 1. And so as we are getting closer and closer and closer to 0, because again, these 1/4 is much closer to 0 than 1/2. So 2/13 pi is much closer than 2/pi. Alright, so as x is approaching 0, I see that, hey, it's going to go between 1 and negative 1, 1, negative 1, 1, negative 1, all the way down. So we don't know what this actually is approaching because that y value is oscillating. Wait, I cannot spell oscillating to save my life. Go figure, math teacher that can't really spell half the time. So y is oscillating between 1 and negative 1. Alright, and if you really want to have a fun time, go look at this graph, and this is math's all caps rage moment where it's like, it's all nice, it's nice, and all of a sudden it's like, in the middle, and then it's all nice again. Sorry, sound effects are somewhat limited in math, but yeah, this is math's definition of all caps rage.